this is actually much more focused on what this group is about, collaborative seed recovery. So let me switch my, here we go. So now we're looking at Xcode. Arrange my windows here. Okay, so you're looking at the actual what's called Blockchain Commons Foundation, and you're looking at the test harness where most of this code is written, but it's built on the actual foundation. So we have a layer called Secure Components, and you'll see that in our repository, and that's where the code for Envelope lives. And then we have BC Swift Foundation, which is where a lot of stuff dealing specifically with cryptocurrency lives. And it's also, a great place to, to write envelope requests and responses. And so one of the applications of envelopes is to have cryptographically strong requests and responses. So the basic scenario that I've been working with is the idea that somebody wants to set up a service where they are allowing the public to come and store SSKR shards. So SSKR is a way of taking your seed, sharding it into, say, a 2 of 3, where a quorum of shares is necessary to reconstruct your original thing. And so you might print out some of them, put them on friends, you might hide some on NFC cards, and you might distribute some of them through what we're calling share stores. And so what I did is I created a skeletal share store. It's all in RAM. It's not actually using a real database. But I wanted to show what an API for this would look like, and even more importantly, what it would look like using envelopes. So,
Nicholas, you had a quick question?
Mm-hmm. Yes, sorry, but right now on the presentation, all I'm seeing is a YouTube page. The last screen
that's interesting.
No, I'm seeing. Yeah, I'm seeing the correct page. I'm seeing an Xcode page, but we can refresh.
Okay, I just tried resharing, so I don't know if that helped at all. But my Xcode window is what's outlined in green right now, according to Zoom. So that appears to be what I'm broadcasting.
Okay, thanks. I think it's refreshing on my end as well. Thanks.
Okay, very good. All right, so this is basically, again, this is all test code. This is not part of the main library here. The main library in this case is BC Swift Foundation, and we're mostly playing in the actual test harness right now. This whole example store code you're seeing is actually in the test harness, and so but it's intended to give a working example for how a developer that really wants to actually implement one of these share stores might go about it. So there's certain things that are glossed over, certain things that could stay improvement, but I think it's a fairly realistic scenario. Generally speaking, there's limitations like how many bytes can a share be, because basically if you're offering this, if you're doing this in an unauthenticated way, which is part of one of our, well, it's authenticated, but it's trust on first use. So you don't need, and you don't need to be anything other than a public key to store things in the share, and you can store up to 1,000 bytes the way this is set right now. But everything is very cryptographically strong. So various kinds of errors it can throw, and then the actual database. This is the in-memory database. It's just a series of dictionaries that correlate various things. I think that's fairly self-explanatory. But the most important thing I want to show you, and this is the low-level internal API, the Swift interface of Example Store. It's primarily called indirectly by the distributed function called API, which I'll show you in a little bit, which handles authentication of the public keys on incoming requests. So by the time any of these functions are called, the caller must have already provided by signature that they control, proved by signature that they control the corresponding private key. Okay, so that's why you're not going to see signatures involved in this particular part of the API. So the main call that people are going to use is the store share call. This is a trust on first use function. If the provided public key is not recognized, then a new account is created and the provided payload is stored in it. It's also used to add additional shares to an existing account. Adding an already existing share to an account is idempotent, which of course means nothing changes if you do something that you've already done before. And so it takes your public key. This backend never actually sees your private keys at all. So you'll see some reference to private keys later, but the backend of the share store never sees private keys. And then payload data, it could be anything. We're thinking SSKR shares would be a very common use case because those are not really private. You can split your seed up, distribute to a number of people, and none of them, unless they can collude very deeply, can actually put your seed back together. They have to have the quorum. So you give it these things, and it gives you back a receipt. So the next thing is there's has to be a mechanism that if you lose your private key or so you can't sign things anymore, or lose your public key, lose your key pair, then you need to have a fallback mechanism. And so we have a mechanism here called update fallback. Updates an account's fallback contact method, which could be a phone number, email address, or similar. Now, this is probably less sophisticated than it would be for an actual deployed system, so I'm just using a string as the fallback method. So you can make it as complex as you need it to be. The fallback is used to give users a way to change their public key in the event they lose it. It's up to the example store's owner to validate the fallback contact method before letting the public key be changed. So obviously, if a person says they want to change it, you need to send them a text or an email and let them click a link to confirm it. But they need to have registered a fallback method first. So this is the way a user could retrieve their own fallback method. And remember, even though you're putting public keys, these transactions are all going to be signed. So they're not valid unless they're signed. And I'll show you how that works in a moment. So update your public keys. Sometimes you're going to need to rotate your public keys. So in this case, you're providing both the old and new public keys. Changes the public key as the account identifier. It could be invoked specifically because a user requests it, in which case they will need to know their old public key, or it could be invoked because they know their fallback contact method and they request a transfer token. And I'll talk about that in a moment. So they may want to delete shares. So if they have the receipts, which are handed back by the store share, then they can hand one or more receipts that will actually delete the shares. If they hand back no receipts, it deletes out all the shares. Retrieve shares, of course, that's the opposite of store shares. So this is what you do when you want to get back your receipts, and you have the receipts. You don't need the receipts actually, though, because if you don't give it any list of receipts, it hands you. But you have a proper public key that's registered, it will hand you back all your shares. So you don't actually have to store receipts on the user side. And then if the user wants to delete all traces of their account, including their fallback method, they would use this. And this is the method they use to implement the fallback transfer. They provide the fallback string again, the email or whatever, which if it doesn't exist, it won't work. So this is compared to what's already in the database. And then the new public key that they want to use. So this is where then you would initiate contacting them to verify their fallback method and that they intend to change their registered public key. So that's the basic root API here, the internal API. And then I'm going to show you the public version of that. And the public version of that is essentially there's some utilities here, and this is where we get into how envelopes are used. So this is what actual, like clients would use to make a request to the server. They give it some kind of body, which is the actual substance of the request. They give it their private key, then that's for signing only. Again, this never actually traverses to the server. This is used for signing. You'll see where it's used right now. Transaction ID is just in case you want to stabilize that for testing purposes. Because it's a CID or common ID. That's also something Blockchain Commons has a proposal for. Is basically a random number or looks random depending on how it's generated. In this case, it's random. So it creates the transaction request with the ID, the body, and the date, and that's to test and to avoid replay attacks. All these transactions have an expiry date, and then extracts an envelope from that structure. And so now we have an actual envelope. And so, and you can see the envelope. So at this point, we can manipulate using the envelope API. And so I'm not going to recap exactly how envelope works at this moment, but it's basically uses every envelope is a subject, which is a piece of data, and a set of predicate object pairs. So you have subject, predicate, object, and then the same subject, predicate, object, and so on. But each thing, the subject, the predicate, the object, and the whole assertion together, each of these assertions is in fact itself an envelope. So it's recursive. So you can have assertions on assertions, you can have envelopes inside envelopes. So this basically wraps the entire envelope, signs it with the account private key provided by the client, and then encrypts the subject, which is the whole envelope basically, to example store's public key. So this way, as it traverses, no matter how it traverses, whether it's a QR code or over the internet or whatever, the actual request is encrypted. On the server side, we receive the envelope and we want to return one of these transaction request structures. And so the first thing we have to do is we have to decrypt it. And again, this is an envelope. So we decrypt it to our private key, and we're now looking at it from example store's point of view. We unwrap it because it's been wrapped before, so we have access directly to the subject and all its assertions. And then we figure out, based on the subject, what function identifier is being called, which is basically the type of function that's being called. And then we basically reconstruct the body of that. And again, I'm not going. There's a couple layers deeper in the code here. I'm not going to go any deeper than this. And then we have to validate the request. So once we have the original request envelope and we have that transaction request, then we need to make sure that the signature is valid, because the request itself includes the public key, and then it's signed by that private key on the outer side. So you have to make sure they match. And then you also have to make sure it hasn't expired. So there has to be a date in the request, and it has to be recent enough. And then finally, there's handle request. And this is basically the high level call that this is where the server is actually receiving envelopes as requests, and then parsing them, validating them, and then actually executing the various commands of the API. So, and I have a couple prints here. So when actually, when a request is received, it's going to print to the console what the actual request looks like, and you'll see what that looks like in a moment, and then the response. Okay, so so now I actually want to show you how this looks from a kind of a debugger point of view. So I'm actually going to set a breakpoint here, and I have a scenario here. Let's let it start up here. Okay. Oops. Okay. So we're going to assume that we have our two main actors here, Alice and Bob, and they're both clients of Example Store's share store. They don't know about each other's existence. They're just basically parallel users. So they each have a public key. In this case, I'm just creating a private key and then extracting the public keys from that. Oh, this is the actual low-level testing. I actually don't want to do this one. I want to do the higher-level testing, because this is basically the low-level testing to make sure every low-level API works. And so we're going to work through the same scenario. But let me make sure I bring up the actual proper file here. We want example store remote tests. So here we go. All right. So now we're in the realm of envelopes and requests and responses. So here's example store. This is the actual instance of the store in RAM. We're going to set a breakpoint here. So we're going to do the exact same thing in the code I just showed you, but now we're going to be doing it using passing messages and so on. So, so in this case, Alice controls her private key. This is her private key. She's going to store a payload. This is basically just a hex literal, but that could be anything. So SSKR share, exactly. And she's going to get back a receipt for this stored. And again, she can throw this away if she wants to and still access all of her data. But if you want it, it's there. So she creates a request. This is a store share request body, and she says make request, and she hands her private key off. This is to a local API that will then create and sign the request and the payload, and then tells example store this is where you transmit it over the cloud to the cloud. It would handle the request and send it back. There's no private information at all in the request, and then receives the receipt, which then gets assigned up here. So if we actually step through this code here, so you see here's where the request is, and now here's where the server is going to handle the actual request. And here it actually prints out the envelopes. This is the decrypted and validated request. It's the requests and responses are all correlated to what's called a common identifier. This is the request identifier. This is the response identifier, which is the same. So you can match requests and responses. So this is the subject of the envelope. What's in brackets is all the assertions in the envelope. There's two assertions in this envelope, one called body, one called date. This particular assertion says I'm a function call. That's what these double angle brackets around it mean. And I have my own assertions. My own assertions are, this is single angle bracket, means this is a parameter. So this is basically a remote function call thing, conventions. So, and these are all documented in our envelope documentation. Here's the payload, 4 bytes of data, and our public key and the date. So, and so this is what I meant by assertions on assertions. This is a list of assertions. This is a predicate. This is an object which has its own list of assertions. This is a predicate. This is its object. It has no assertions. So this envelope notation gives you a recursive way of looking at how envelopes are structured. And again, I just want to point out that any of these things can be encrypted, elided. You can create proofs for them. It's deterministic, so it doesn't matter what order you as the coder add things to. Everything is sorted internally by hash, so that if you're adding the same data to an envelope, it doesn't matter if you add it in a different order than somebody else did, you will come up with the exact same envelope. So normalization is kind of baked in. So in this case, and all this is based on CBOR at the lowest level, common binary object representation. You can think of it as kind of JSON in binary, but it's actually much more strict and much more easy to deal with on a kind of normalization basis. There are ways of doing deterministic CBOR, and it's also more space efficient because it's pure binary. So the response it sends back is, it's tagged as a response. It's the same identifier, so you can correlate it. And here's your result. It's a receipt, which is a CBOR object. And so that's the first call. And so Alice has basically stored a share. So now Bob comes along and he does the same thing. We're not going to belabor this. He has a private key. This is his payload. He's going to do the exact same thing. And basically, so here's the actual Bob's. Okay, that looks pretty much identical to Alice's. So, so now Alice is going to retrieve her share. So she creates a retrieve share request body. Again, she only providing her account private key to the local API so it can sign it. And then she provides a list of receipts that she wants. She only has one share. She's going to provide that receipt. And then the server basically responds it, and then 10 seconds passed. So that's her expired request. So I basically made it so that right now it's actually using literal seconds. I don't have it in the test harness, but since I took longer to explain that than it did, so that's what happens when a request times out. So let's just proceed on to Bob and let him retrieve his share. Hello. Oops, where's my? Okay, I don't know what happened there. Okay, well. I'm gonna jump right back into this. Not sure where my program counter is, but there it is. Okay, all right. So Bob retrieved his share successfully. Here it is. There's the request and there's the response. Alice is now going to store a second share under her account. And again, there's the request and there's the response. And so the result is a second receipt for Alice. So she is going to extract that, store that for later. We'll use it. So Alice is going to now test by requesting a second share. There's the request, there's a response, there's the share back. And so now Alice has basically made it a later time, wants to retrieve all her shares. Maybe she hasn't saved the receipts or whatever. So she's just going to provide just her public key as her identifier signed by her private key. And then just send that off. And then that's going to send back both of these. Now these look similar. Basically, one of the rules of envelopes is you can't have two identical assertions. These aren't actually different, the same, because the data is different in each case. And of course, if you think that's a problem, there's many ways that it's not a problem. So just ask me. So she's just basically going to compare what she knows to be the proper results with what she got back. That's what that line is for. That succeeds. None of these tests should fail, obviously. So Bob is now going to attempt to retrieve one of Alice's shares. So basically, he has a receipt from Alice for some reason, and but he doesn't have Alice's private key. So he's going to say, make a request with his private key, but Alice's receipt. And here's the response. And as you can see, the latest response is user mismatch. So basically, it's going to double check that got that correct thing. So that's not allowed. Or some rando attempts to retrieve all the shares from a non-existent account. Obviously, got to test these edge cases. So here it is, unknown public key. There's no account by the public key. Alice stores a share that she's previously stored. This is idempotent. So if you store something 3 times, it's the same thing. You get the exact same receipt. In fact, it's checking to make sure that it gets back is the exact same thing as receipt 1. So that's all deterministic. That works. Alice deletes one of her shares. So here's the delete shares request. Here's the receipt she wants. She's going to delete her first share. So boom, boom. This doesn't have any other result other than okay. And so it's just making sure the result is okay. And then also she's going to make sure that there's only one payload coming back now. So she's going to recompose a retrieve shares request for all of her shares. She tests it. And there's only one share now, because before you saw 2 shares. And going to double check that. Okay. Alice attempts to delete a share she's already deleted. So this is also idempotent. So if you request the deletion of a share, it says, okay, it's already gone. So trying to make basically as many things idempotent as possible. So now a little bit about fallback methods. So Bob basically is concerned that if he loses his key, he needs some other way of of recovering his shares. So he's going to update his fallback request, and he's going to just set it as to an email address. Server says okay. Then he's going to retrieve his fallback request. He wants to double check it. Maybe later time he wants to see if he stored it. So that actually hands back the result. Alice has never set her fallback contact method. So if she tries to retrieve her contact back, she gets an error, no fallback. And then someone attempts to receive a fallback for a non-existent account. Again, this is just testing like edge cases, unknown public key. So now Alice is going to update her public key to a new one. She says maybe time to rotate keys. So this doesn't require anything other than, but it does require your old private key and your new private key. So here's your new private key. And then she's going to create a request and response. It says okay. And then she's going to try to use her old public key to retrieve the data. So this is Alice private key, not Alice private key 2. So she's going to generate the same request she's done to do it before, but this time it comes back as unknown public key. There's no account with that public key anymore. So Alice has to use her new public key. This is Alice private key 2 to put into and sign the transaction. There it is, and there's her one share. So if Bob loses his private key, so he wants to replace it with a new one, so he's not going to have his old public key to use in this scenario. So he's going to request a fallback transfer. And so he's going to provide a wrong email address, hard to remember those, with his new private key. And it's basically going to come back and say invalid fallback. That's not your fallback. I can't send you something at that to test if you're really Bob. Okay, so now Bob requests a transfer using the correct fallback. So here's the request, here's the response. It says processing. This is because the store must now initiate asynchronously using the fallback to verify the user's intent to change their key and only change it if the verification succeeds. So that's as far as Bob can take this at the moment, and then he has to go, enter a CAPTCHA or click a link or something like that. So let's say Bob never actually bothers to do that. So he just wants to, finish up here. So he's going to use the delete account request. So he creates the account request with his current private key, which remember he never was able to change it before. And therefore it says okay. And now he's going to try to retrieve his share. Just double check it's really gone. Unknown public key. And finally, also all traces have been gone. So his previous fallback is also gone. And that's it. So I don't know why it says test failed, but I'll figure that out later. But as far as I can tell, everything I wanted to show you worked. So